primarily we got this room because the other rooms is much more.
So thank everyone for coming today to the Carbon Cycle 2.0 LDRD seminar. This is our first live webcast version too, so hello to the internet audience. My name is Melissa Summers, and I coordinate the Carbon Cycle 2.0 initiative at Berkeley Lab. And I just wanted to make a couple of quick announcements about upcoming events. Next Thursday, we'll of course have our next in the series of seminar speakers. It's going to be Cheryl Kerfeld from JGI. And we also are going to have an event later that day, this is a week from today, with Ramesh, Ramamurthy Ramesh, who is the director of the Sunshot program at DOE. So he's in town and he's going to give us an update on everything that's going on in solar at DOE. So hope to see you all there. So for today's event, we're very excited to have Ashok Gadgil, who's the division director for the Environmental Energy Technologies Division, and his co-presenters, who are both students with him. We'll have Jennifer Jones, who is a PhD candidate in mechanical engineering and also was awarded an NDSEG fellowship, along with Kathleen Lask, who is also an NDSEG fellow and an NSF fellow in the Applied Sciences and Technology Department. And she's also a PhD student. So with that, I think Ashok will lead the presentation.
We went away from, it went to edit mode. There we go. Thank you very much. So thanks for the introduction. So this is a project which is a Carbon Cycle 2.0 LDRD, but it started a little late because we were not planning to do any of this work. We were focusing on wood-fired stoves for Darfur and Ethiopia and so on, and pretty much at the last minute we had, in the middle of 2010, we had this disastrous earthquake in Haiti, which killed at least several tens of thousands of people, if not a few 100,000 people. The reports vary. I think the government still is saying 400,000 people died, and other groups earlier agreed, but it doesn't matter. There's a big disaster for sure. And we put together very rapidly a large team of people who worked on this project. And today, in addition to me, Jennifer Jones and Kathleen Lask will complete the presentation. But the startup of the background is in January, this was a catastrophic disaster for Haiti. As you can see, the buildings were built not to earthquake standards to withstand any earthquakes of any kind. So there was enormous loss of life. More importantly, there was several 100,000 people were rendered immediately homeless in a very short span of time. And that, you can see that you can't occupy buildings like these or this building has entirely pancaked down. And that was common throughout the region. So effectively, people essentially started living out into the street, and they started living in little tent cities that came up everywhere. And they themselves were precarious, and there was no running water, there was no electricity, no food, fuel, none of the stuff that you would expect. But the international NGO community responded rapidly and started shipping whatever was essential. One of the famous pictures that you might have seen, which we are not going to show in this slideshow, is the satellite photograph of the international boundary between Haiti and Dominican Republic. If you Google that particular satellite picture, or there are many people show that picture from aeroplanes or satellites, that is a stark contrast where at the international boundary, the Haitian side is mountainous but completely shaved bald of any trees. There's only little shrubs or grass left. And the Dominican Republic side of the national boundary is lush green forest. And that happens because there is no protection on the Haitian side for trees getting chopped down, turned into charcoal, and that's the primary fuel that is used by Haitians. It's only the rural, extremely poor populations in Haiti that use wood. Everybody else uses charcoal. Street vendors use charcoal, restaurants use charcoal, households use charcoal, rural as well as urban. Charcoals are substantially less efficient because you lose a big fraction of energy content of wood when you convert wood into charcoal because you lose all the volatiles. So you lose even if the efficiency were the same, you are going to use more wood if you are going to go by the charcoal route. So one of the issues that came up during the reconstruction was, can we at least give these people more efficient stoves of some kind so that this complete denuded landscape could have some environmental hope of coming back to life. Of this 85%, my guess is maybe 80% use charcoal and the 5% are the poorest who can't afford it. Charcoal is sold in the streets, and the idea was how do you rebuild in a way that produces more efficiency in cooking. So we were approached as LBL by Senator Benjamin's office saying, you guys are known for doing some work in stoves, why don't you figure out a way in which the NGOs during their reconstruction effort will do something that is the right thing to do for reconstruction of Haitian households. So that was in March, and next month we organized this LDRD saying, let's use internal lab funds, let's see what we can do. So the goal then was to do a low-cost, fuel-efficient cook stove, identify one that emits less pollutants than the rudimentary cook stoves they use. And here is an example of what they use. This is the charcoal stove used by hundreds of thousands to millions of Haitians in their homes. This is individually made by craftspeople working out of garage scale shops using hand tools. This lasts typically between 6 months to 1 year, and then it rusts through because the iron sheets just rust through at the temperature at which it operates, and then you get a new one. So this is what goes on a routine basis, and there is no quality control or no standardization, but we bought back a couple of these so that they are a baseline. And then at the same time, when we organized this fact-finding mission, we had Keja Booker, who was a candidate, doctoral candidate, Robert Cheng, who is a senior scientist in Environmental Energy Technologies Division, and Scott Sandelon is an engineer who had worked on the Darfur Stoves project, but he now works at a startup. And we approached him saying, since you have worked in the field, you have worked on stoves, could you go along? The goal was to identify what could we best do to help the reconstruction effort regarding fuel efficiency of cooking. And what they found was, here is just an example of rice and beans, which is their main food. This is now being cooked on charcoal stoves in a communal kitchen. What I would like you to note is that the communal kitchen stove, the rectangular box with charcoal there, is exactly the larger version of this box that you saw. That the pots are resting directly on the burning embers of coal, cooling them, causing a lot of carbon monoxide emission. You don't want that to happen, but that's what people do. They put a pot of boiling water on the coals, and of course you get a lot of CO as a result when you quench the coals, and the efficiency is not great. So this is a little a copy of a slightly improved stove, a Mirac stove, but locally made, and we tested that too. So we found that what the NGOs were doing were very interested in fuel efficient stoves. People were refusing to move away from charcoal. They said this is it, because wood means smoke inhalation, it means poverty, it is not an aspirational target. Our aspirational target is to stay with clean cooking. For them, clean cooking meant you don't get smoke in your hair and eyes and clothes. Charcoal delivers that. So the NGO said, forget it. You're not going to move away from charcoal. And they also said there are a dozen models being promoted, and each NGO essentially was being quoted by various suppliers of charcoal stoves of variety of quality, and NGOs had no way to find out if the claims were any good. We had a case where a couple of containers, the shipping container loads of stoves were brought in by an NGO based on a web-based claims, and it turned out to be complete junk. And all the money was wasted and all the stuff was just thrown away. So our team determined, and NGOs agreed, that the best thing we could do at this time was not to design one more stove. There were enough stoves being promoted. Our job in this particular situation would be to provide an unbiased and credible performance assessment of different fuel-efficient stoves compared to the baseline. And that's something that they were unable to do. They don't have the equipment, technical expertise. They can't organize the testing there, though they should have done so there. So we said, fine, this is what we could be useful to do, that's what we will. Okay. Now, this is getting stuck for some reason. I don't know. You know what's happened? Good, got it. Now it should work. Good. Right? So that was the LDRE goal all along, 2010, April when we started, and came back here with samples of Haitian coal, charcoal, samples of a number of stoves that were being promoted. And then our goal was to do baseline testing, okay? So this is something I need to pause and say, because it's not on the text on the slides. Performance of a stove really depends on many, many factors other than the stove itself. It depends on the skill of the cook in tending the stove. So you need to train testers, and when you're training them, it takes a lot of time. And all those tests have to be thrown away because your testers are under training. Once your testers have been trained, then of course the fuel matters, so you have to have consistent fuel, presumably similar to the one in the field. Then the stove matters, and we are going to use different kinds of stoves. Then the pot matters. The pot has to fit the stove in a particular way. If it doesn't fit, the performance will be different because the heat transfer will be different. Okay? And then of course what matters is what kind of food is being cooked. If you're frying some food, it's going to be an endothermic process, so you got to do a high-powered burn, and then the performance of the stove is going to be different than if you had a low-power burn where you're only simmering some water just to cook rice, maybe. Okay, so effectively, what the stoves community has done is develop a couple of different tests. A standard test is called a water boiling test, also sometimes called an international water boiling test. It's an international standard test that does not pay attention to all the stuff I mentioned. It says, take an aluminum cylindrical pot of this diameter and this height. Put in that pot this amount of water and put it on the stove and bring it to boil and do this, do this, do this. So if you happen to be frying or baking or roasting, sorry, that's not what WBT is about. WBT is about having an international standardized comparison from stove to stove. And it may not therefore reflect what actually happens in the field or in the real kitchen. But at least you can compare across the board in terms of what stove is tested in Thailand, what is tested in the US, what is tested in Haiti. This test is, on the other hand, culturally specific, is specific to the kind of food that is being cooked, is lab reproducible surrogate of local cooking practice or a local cooking cycle, but precisely because of that, is not going to be the same across different cooking styles or different food groups or different continents. So we decided to do both. We said we'll first do the water boiling test because they're straightforward and easy, and then we'll do the controlled cooking test, and that incorporates the culture-specific cooking practices so that the results of this would be a lot closer to what you would expect to find in the field. But now I'll hand this over to Jennifer to discuss the results from WBT.
could you hold it for a second?
Okay.
Right. Great. Hello, thank you all for coming. Can you hear me?
Yep.
A little bit louder? Okay. So I'm going to talk about the water boiling test and the results that we got from that test, and then I'm going to hand it off to Katie, who will talk about the controlled cooking test and our results for that. So specifically for the water boiling test, we were shipped a series of 5 stoves from local NGOs in Haiti, and the stoves were either currently being used in Haiti or considered to be used in Haiti. And the stove that Ashok brought down here, the traditional stove, is on the left, right there. And then in a previous picture, he had also talked about the Maroc, and this is a local improved stove, and that's the Maroc stove. And then three other stoves were used: the Eco Richo, Proxy, and then the Stove Tech. So just to describe a little bit more about the water boiling test, it essentially consists of 3 main phases: the cold start, hot start, and simmer phases. And in the cold start, you start with a cold stove and a cold pot and a certain amount of water, 2.5 liters, and that water is brought to a boil. And then for the hot start test, the previous hot water is dumped out, but the same hot stove and the hot pot is used with a new batch of tap water, and that's brought to a boil. And then immediately following that, the same stove and the same water is simmered for about 45 minutes. And so the first 2 are high power tests, like Ashok was talking about earlier, and then the third one is a low power test. So each water boiling test for each stove consists of all those 3 phases. And then at the bottom, if you want more details about the specific equations and the methodology of that test, you can find it at this address here. Or you can also just Google water boiling test protocol. So I'm going to go through some of the results that we found now. And what we did for the water boiling test is we looked at different performance metrics. One was the time to boil. Another one was thermal efficiency, specific fuel consumption, and then we looked at different emissions. So we looked at the emissions of carbon monoxide, carbon dioxide, and then the ratio of carbon monoxide to carbon dioxide. So first I'm going to talk about time to boil. And so what you're looking at here is the plot on the left is for the cold start, and the plot on the right is from the hot start. And we have the time on the y-axis, and then each of the stoves on the x-axis. And what's plotted is essentially the mean value of all the tests for the time to boil, and then 95% confidence intervals. And the traditional stove, this one right here, is listed in this gray color on the right. And so what we're really trying to do is we're trying to look at how each of these improved stoves compare to the traditional stove, and then to see if we have any best performers in each category. So for time to boil, generally we had the Stove Tech did the best for the cold start, and the Maroc did the best for the hot start. You'll notice that for our first round of tests, our error bars are pretty large, and that's because we had lower sample sizes to start with, because we didn't know how many we needed to be able to always determine statistical significance. But that was one of the lessons that we learned and improved upon for our controlled cooking tests. And so we did more tests for the next phase, and that contributed to better results. So next is plotted the thermal efficiency and the specific fuel consumption of each of the stoves. And again, we're comparing all the improved stoves here to the traditional ones. And so the Proxy generally performed the best here. And over here, the Stove Tech. And for the water boiling test, we weren't always able to determine statistical significance, but we had general performance that were better than others. And then looking at emissions, you can see that the several stoves actually performed worse than the traditional stove for the carbon monoxide emissions. And that was the StoveTech stove here and the EcoRicho. And then for the ratio of carbon monoxide to carbon dioxide, which is essentially a metric of how complete the combustion was. If you have a low number there, that's desirable. So the Maroc stove really did well in that category. But as you'll notice, there wasn't a clear winner for one stove in each of the categories. And the traditional stove performed faster in terms of time to boil, but many of the improved stoves, actually all of them, performed better in efficiency than the traditional stove, so that was really positive. And then just to summarize, the best stoves in terms of the efficiency category and the emissions category. And then in the report that we put on the LBNL Cookstove that you could look up here if you want more details, we also listed how the stove's usability compared with a traditional stove. And so what we're hoping is that this information is going to help future stove designers to be able to compare the current stoves in operation and see how they perform with the traditional stove, and then take the good parts of each. And then, like I said earlier, that one of the additional lessons that we learned is that we needed more replicates per stove, and that's something that we did for the next round of testing. So I'm going to go ahead and hand this off to Katie, and she's going to talk about her results from the controlled cooking test.
Hello. Can you hear me? Is this good? Okay. I'm going to talk about the controlled cooking test that we did. Likewise, to the water boiling, we used local Haitian pots for all the tests. And we have 4 of the 5 same stoves from the water boiling test. The StoveTech was withdrawn because they decided to go in a different route. And the EnviroFit was added. It showed up slightly too late to be used for the water boiling test, but we did do it for the controlled cooking tests. So as Ashok mentioned, CCTs are specific per cultural region, so we had to develop one for Haiti. The LBNL original fact-finding team took many detailed notes on cooking practices there, and along with local NGOs and people who had spent a long time doing field testing, we developed a general protocol method. The main meal that we decided to focus on is called sospa. It is rice and bean sauce with vegetables, as shown here in this picture. It's a common daily meal in Haiti, so we felt it was a good reproduction for our protocol. The procedure involves 3 main phases: beans, vegetables, and rice. The beans are brought to a boil and cooked on simmer for about 20 minutes, well, for 20 minutes, and then taken off. The vegetables are put on next. The vegetables are represented by a pot of boiling water, as vegetables are primarily made up with water. It's an endothermic reaction, and therefore you don't actually have to boil the vegetables in order to be representative. When that was finished, the beans were yet again brought to a boil, and then the rice was added. Everything was brought to a boil again and simmered for another 20 minutes. In the end, you get a delicious pot of rice and beans. We added garlic and salt and made it very tasty. Precise amounts of ingredients were used for each test, so 500 grams of beans, 1,000 grams of rice, 2,500 grams of water, to make the test as reproducible as possible while also reflecting upon cultural cooking practices. To get into the results, as Jennifer mentioned, we attempted to do many more tests for the CCTs, and the specific fuel consumption error bars are a good example of that. For this, all of the stoves had between 8 and 12 tests for specific fuel consumption. The specific fuel consumption that we did is the grams of charcoal burned over the kilograms of food cooked. That's how it was calculated. And as you can see, the traditional stove used far more charcoal than the other improved stoves, as would be expected. Out of the other 4 improved stoves, Procti performed the best with EnviroFit close behind. And yes. As far as emissions went, the traditional for CO emissions produced the most CO emissions, and EnviroFit performed the best, the least amount. And then the CO2, which indicates the amount of complete combustion, the results were far more, they were closer together, but the EnviroFit still performed the best overall. The Procti in both graphs appeared to perform second best, but it had a larger amount of fluctuation, and so therefore it's hard to be conclusive with those results. The traditional and eco ratio, however, appear to have the worst combustion. In conclusion, the traditional stove consumes more fuel than the other improved stoves. It's nice to have that conclusive. The efficiency winners, the Procti and the EnviroFit, and the emission winner was the EnviroFit. As with the water boiling test, we did usability studies. We had a new group of testers, and they offered new input. And that will be included in our report, which will be published soon, hopefully. Yes, and will be published and posted on that website. Now I hand it off to Ashok again.
Actually, I just wanted Katie to finish this, but she says, no, you have to finish it. So, okay. It is a surprise, actually, that the so-called fuel-efficient stoves actually perform better than the traditional one, as the last slide, the top one shows. Okay, you'd be surprised. We have tested stoves made in India which claim to be fuel-efficient, which are as bad as three-stone fires. And that comes from the fact that there is not enough rigorous third-party independent tests carried out for something that affects lives of millions of women and affects smoke inhalations of millions of women and affects deforestation in places like Haiti. So this might look like a straightforward, obvious something, hey, how could it be any different? But it is a relief to find some conclusion like the first bullet up there. That's not always the case. It is indeed the case that NGOs really don't have the capacity to do the technical testing. Their skill set is very different. They are much more skilled in responding to disasters, in figuring out how to set up supply chains, how to do humanitarian work, how to do the social science side of it, but not the technical side. And when we ask them, why don't you do this? It's so obvious, so simple. Go take a weighing scale and do the test. No, they don't want to do it. So we actually played a valuable role. It was entirely worth our while. We got lots of thanks from NGOs to whom we have emailed our report already, both to the stove manufacturers or makers as well as to NGOs. So they appreciated what we got, and in addition to having the thing posted on the web, which means everybody else gets to see it too. So now that we are done with our emergency short pulse response, other organizations, such as the Partnership for Clean Indoor Air, which is led by EPA in their technical testing phase, they are continuing with long-term stove tests for Haiti and elsewhere. And we concluded our LDRD-funded work as of end of September. We'll put the second report out, we expect, in a week or so. and then we are done with this particular piece of our stove's work. And it was, as you can see from the second slide, a very large effort that involved maybe a couple of dozen people who practically dropped everything and contributed to making a useful response based on technical knowledge that a lab like ours can bring to bear on national emergencies like what Haiti experienced. So I would like to stop there and take questions. So, yes, please. Yeah. Thank you. Yeah.
Did you learn anything about the mechanical characteristics that affect the efficiency of the different stoves?
Sure, I'll repeat the question, that makes it easier. The question was, what did we learn about the mechanical characteristics that affect the efficiency or even the emissions also of the stuff, right? So a couple of things came off the top right away, which is if you put a cold pot on charcoal that's burning, is going to quench the charcoal and it becomes a very efficient producer of CO. So if you wanted to reduce CO, you ideally want your pot to sit a centimeter above the charcoal bed. That has been difficult to do because there are a number of people who have built stoves which have a little grate or a grill that keeps the pot above the charcoal bed. But if you do that, then the trouble is the charcoal bed begins to sink as the charcoal burns away. And as the gap increases, you get more and more air that doesn't transfer heat well to the pot. So the solution effectively is people just put it on the charcoal bed. So if I wanted to issue a challenge for ingenuity, is how would you design a stove, a charcoal stove, where the pot, a load-bearing support on the pot, sits above the charcoal but at some fixed distance, so that you're just having a centimeter clearance between the top of the burning charcoal bed. But as the charcoal burns, you don't want the bed to keep on sinking, and you want it sufficiently easy to add charcoal pieces, because as you can see from a stove like this, effectively what they do is they load this with charcoal bed, put the pot on top, and as the charcoal burns, the pot keeps on sinking in. And for them that looks like, hey, this is pretty good, right? But the CO production on the other hand is pretty high as a result. So we would like to design something that is better than that, and we thought of things which got too complicated because the cost of the stove needs to be really low, the durability needs to be longer than this. This is 6 months to 1 year. So that is one thing we learned. The second thing we learned was if you have stoves that have thermal mass in them, because some of the insulated stoves were made with insulation in the form of insulating bricks, porous bricks. So that's the difference between a hot start and a cold start. For a stove like this, hot start and cold start makes no difference. It's so little thermal mass. But if you had a thermally massive stove because of the insulating brick, then that begins to make a difference. So that helps only when you are developing a stove to the test, because my test was water boiling test. And I had to do hot start, I had to do cold start, right? And I had to do simmer, and then I had to accumulate what was the total emissions and what was the total fuel burn. But if I'm doing CCT, then I can be actually making the stove true to the CCT. Because now I'm saying, I don't care about this international test. I mean, that's good. That's a side business. The important thing should be I design a stove that performs for the women who are doing the cooking. So what is the controlled cooking cycle? And I should design the stove that is true to that goal rather than the water boiling test. But because it's the water boiling test that's the universal metric, some of the stove designers designed the stove to the universal metric, even though the universal metric is not a good reflection of what the women are doing in the real world. So we found that dissonance too. And that happens because for every culture, somebody's got to go out there with weighing machines and measuring parts and so on to find out what is going to be your control cooking test for Haiti or for some corner of Mexico or whatever. So long as that remains a variable, people kind of try to be conservative and they say, let's stay with control cooking tests. And that's sometimes training for the wrong test. Yes, please.
I noticed that the time for the traditional stove
Exactly. Good point.
Did it change behavior of the women?
Oh, he certainly did. So the question is, he noticed that correctly, that the time for cooking or time for bringing to boil, water to boil, for the traditional stove is noticeably shorter than for the efficient stove. And effectively what that is reflecting is that this stove has a much larger fuel bed, and if all the coal here is ignited, you got a much higher thermal power now. This is 5 kilowatts, right? Going into the pot at some efficiency. The other stoves with insulation and smaller bed are maxing out at maybe 2.5 kilowatts. Even though they are more efficient, still the power into the pot is net power less because it's a smaller stove, smaller fuel bed. So we got pushback from not only our testers, but even the women in the field who said this might use less fuel, but we don't have time to mess with this. We want something that cooks fast, and we are out of cooking back to looking after our kids or washing clothes or earning a living. So a substantial feature, important feature of the stove from the end user's perspective is not just the amount of fuel used or not thermal efficiency alone, but time to cook. And that is reflected in a large bed here, which actually has a high power all the time, which means it does waste fuel because it's designed to cook quickly. So there is that trade-off as well. And those of us who don't pay attention to user preferences will simply end up saying, well, you know, this little stove that cooks on a little candle is going to be the most efficient. So nobody will take that stove. That's the downside.
Oh,
Yes.
Can you wait for the mic?
As a follow-up to that, shouldn't you then scale the pot as you scale, the furnace?
Excellent point. So Henrik is saying, why don't you then scale the pot? So now we have a smaller pot. The trouble is the family doesn't get smaller. The family is fixed size. So now you got to worry about what do you do, right? That is one problem. The second problem is, you are exactly right that ideally I should be selling a stove-pot combination. Not simply saying, throw out the old stove and put in a new one. But the pots last a long time and the family has invested in it. The stove, on the other hand, the traditional one, goes to rust in 1 year. So I have a natural way to slide in a more efficient stove at that time. But it's hard for me to tell them, throw away those pots. They are not going to be useful with the new stove. So it is a difficult choice.
But would one not expect similar results in your two tests? In other words, the water boil test and the CCT test should give the same similar results in terms of thermal efficiency. Because even in the water boil test, the main thermal load is the boiling of water.
Yes.
As it is in the CCT test.
Right.
Therefore, if your efficiency is defined as useful heat delivered to the pot divided by fuel burn, the two tests should give the same result.
Good question. So the question is why, aren't the CCT and the water boiling test, why aren't they giving you the same results? Okay. As you notice in the CCT, we use actually raise the temperature of water, boil the beans, separate the beans, keep the hot water there, and use the same hot water to add to the final mix of rice and beans. Okay? So that more accurately reflects what happens in the real cooking cycle. Whereas in the standard water boiling test, you bring it to boil from cold start, throw away the water, put in again cold water, again bring it to boil, and then hold it for 45 minutes, no matter what the cycle. So these differences ultimately matter, because one is high powered, one is low powered. The power performance of the stove also matters. The other thing I should say, the charcoal stoves are notoriously difficult to control. Unlike a wood burning stove where you can just stuff more wood and you get more power, and you pull out wood or don't feed the stove enough, and it goes to low power, right? Because you have fewer sticks burning. This thing is not like that. You got a charcoal bed of a given size. You light the bed, and this is it. The only control you have, and some of the stoves do have that control, is a door on the bottom. Let me see. Where does it go? One of the, here. Some of these stoves have a door at the bottom like this. That door gets incredibly hot and is impractical to move when the stove is lighted. So there are practical problems in that operation. In theory, it works very well if you got asbestos gloves when you're an engineer. But when you're a woman in Haiti and you saw how those people live, they don't have anything but a rag to hold their pot. So there are problems with controlling the airflow to control the power of the burning charcoal bed as well. So it is a tough engineering problem, besides a problem with a lot of inherent variability. And as we discovered in our first test, our error bars are very large, which means that our averages are not as credible as we would like. So that's a separate lesson we learned from the testing. Yes. Sorry.
I was wondering if these error bars also include variations in within each brand. So if you take 10 traditional stoves and then ran the same tests, because you said they're all handcrafted and they could be different, so you would expect a pretty large scatter even within.
You're absolutely right. There will be variations from stove to stove as well when they're handcrafted. The only standard stoves we have is everybody else here, right, in this lineup. This is the one that's going to vary every time. We don't have the wherewithal, the resources to take 10 of those and test each of them 10 times. So we just took one off from the market.
I was also worried about the spread. What is boiling? Do you put boiling chips in? Is it the first time you see a bubble, or is it full boil, or how do you judge it's boiling?
I think the WBT specifies how you judge boiling. You have to bring the water to a roiling boil, or you have to stir it. Yeah, of course, temperature, and then you correct it for height as well, not just visually. So you measure the temperature, and during the calculation for WBT, which is on the website that was shown, you correct for the air pressure as well.
Okay, but I'm worried each can boil different because you need nucleation points, and so do you put boiling chips in the water just to make sure they're all sort of going to boil at the same point?
Oh, I see what you're talking about. Now let me back up and explain. He's asking whether we put a boiling chip, which could be a piece of pumice stone or something, to nucleate the boiling, so you never get superheated water, and then instantly everything has a roiling boil. That's what he's asking. No, sir. We don't put boiling chips in the water. The pots are pretty crappy. They have a lot of roughness. There's plenty of nucleation. Okay. We are using real pots. We got them from the field. Okay. Thank you, everybody. Thanks a lot.